Welcome to the another video on VLSI design course. In this video, we are going to discuss on pass transistors and transmission gates. So we all know that pass transistors, either NMOS or PMOS, will work like a pass transistor that transfers information from one point to another point. Here, the strength of the signal in case of a pass transistor is measured by how closely it approximates to an ideal voltage source. So, ideal voltage source in the sense, for high level it's going to be VDD, and for low level it's going to be 0 volts or ground. So, this is an ideal voltage source. So, the signal strength should be very close to VDD or it should be very close to 0 volts. So then we say that the strength is stronger. So the stronger a signal, the more current it can source or it can sink. So the signal what we expect should be as strong as possible here. Then we say it is a good pass transistor. The power supplies, normally it is VDD or ground that we call as rails, are the source of strongest ones and zeros. Generally we interpret VDD as logic 1 and ground as logic 0. Okay, so we expect the strongest ones and strongest 0, provided if VDD is typically it is going to be the 5 volts and ground is going to be the 0 volts. So then we say it is a strongest ones and the strongest 0. Okay, so let us now interpret what we mean by the strong versus weak with reference to the NMOS and PMOS transistors. So let us analyze this practically, but before that let us have a overview of NMOS transistor, how it behaves to the strong 0 and weak 1 or degraded 1. So basically NMOS transistor is good at 0, so we say it is a strong 0. That means it can pass 0 level from one point to another point. Therefore the NMOS transistor is a perfect switch when passing a logic 0 from one point to another point. However, NMOS transistor is not good at 1. So we say NMOS transistor is weak at 1, or we can say it degrades 1, it has a degraded 1. The reason for this is it behaves like a imperfect switch when passing a 1 from one point to another point. So in summary, we can say that the N-channel MOSFET is a perfect switch while passing a 0, logic 0 or 0 volts, whereas it is an imperfect switch while passing a logic 1 or 5 volts. So these things we'll analyze practically, and we will let you know how exactly the NMOS passes 0 very well, and how it is going to be imperfect while passing logic 1. Okay, let us have a overlook of a PMOS transistor. Similar to the NMOS transistor, the PMOS transistor it behaves quite opposite to the NMOS transistor. So PMOS transistor is going to be strong at 1. It is a perfect switch while transferring while passing logic 1 from one point to another point. However, the PMOS transistor is going to be an imperfect switch while passing the logic 0 from one point to another point. Therefore, we can call PMOS transistor degrades logic 0, or it is weak at going to be logic 0. Okay, so these things let us discuss with the help of transistors. Let us consider NMOS and PMOS transistor, the practical way how it behaves, and we'll come back to this switch behavior of this. So let us go through the refer here. Let us draw the NMOS transistor. So we have NMOS transistor here. So we have a gate here, and the one side we have a source. So other side we have a drain. Okay, so such source side we interpret as input, and drain side we measure the output. And let us tie this gate to the high voltage. Let let us tie this gate to the high voltage, which is plus 5 volts. Okay, now let us see how it behaves. Let us have here a variable voltage. So here let me connect a variable voltage here. Variable voltage here. So our goal here is to apply a voltage, okay, in the manner of a step, but we don't apply a step voltage here for from 0 volts to 5 volts. Instead of we apply voltage in terms of uh, Vs voltage as 0 volts and 1 volt, 2 volts, 3 and 4 volts, and lastly we have 5 volts. Let's assume that this NMOS transistor has threshold voltage of 1 volt. So let's assume that NMOS transistor threshold voltage equals Vt equals 1 volt. This is an assumption. So we assume threshold voltage of an NMOS transistor. We can also label this as VTN. So this is the threshold of NMOS transistor, and this is the voltage that is applied at the source, and the gate is tied at 5 volts. So let us here write it Vg is fixed at 5 volts. Now let us see that what will be the VGS. Let us write here the voltage VGS at Vs as 0 volts. Okay, so we all know how what do we mean by threshold voltage. So threshold voltage is the minimum voltage for the transistor to turn on. So whenever we want to make this transistor to turn on, so we need to apply here a minimum voltage between the gate and source. This we call as VGS. Okay, the minimum voltage that is applied between the gate and source to turn on this transistor, that is the threshold voltage. Typical value of threshold voltage is 1 volt for the n-channel enhancement transistor. So at least 1 volt we need to apply here, okay, for this device to conduct. So we need to apply 1 volt here. This is the minimum voltage to be applied for the device to conduct here. Now let us start with 0 volts and see that what will be the output here. So when we apply source voltage as 0 volts, here source as 0 volts, so the VGS is going to be 5 volts. Okay, VGS is going to be 5 volts because 0 volt here. I'll just remove this minimum voltage. Okay, so 0 voltage is applied at the source, and now VGS is going to be VG minus VS. So VGS is VG minus VS. So for the 0 volt at Vs, this is 5 volts minus Vs is at 0 volts. Therefore, VGS is going to be 5 volts. So what we got to know is VGS is 5 volts. So device is completely, it is on. It is heavily, it is on. So we can say that NMOS, it is on. And let us go with the series of voltage here that is shown here. When Vs is equal to 1 volt, when we substitute here Vs as this remains same, Vg remains same, this Vs is going to be the 1 volt. So VGS becomes now 4 volts. So this is 5 volts minus 1 volt becomes 4 volts. Now 5 it has changed to 4. When this is going to be 1 volt, so the VGS is going to be 4 volts. And you can observe here, as Vs keeps increasing in this manner, VGS keeps decreasing. So you can see for 0 volts we have 5 volts, for 1 volt of gate we have VGS as 4 volts, for 2 volts we have 3 volts, okay, 3 volts as VGS. For 3 volts of source voltage, when we apply here 3 volts, 3 minus 5 minus 3, that becomes 2 volts. When Vs is going to be 4 volts, VGS becomes 1 volt. You can see here now we reached a minimum voltage required for the device to conduct. So in all these values of VGS, transistor remains in on condition. But when Vs reaches 4 volts, VGS is going to be 1 volt. So therefore, so it is at the verge of the off. Okay, so still it is on, but the moment we cross slightly, this becomes off. When VGS is equal to Vs is equal to 5 volts, VGS becomes equal to 0. Okay, so Vs is 5, 5 minus 5, that becomes 0, then the transistor will be turning off. So that means when we apply here voltage Vs voltage very close to say 4 and above, the transistor will be turning off and it will not allow the 5 volts or the more than 4 volts to pass from input side to output side. So therefore we say that NMOS transistor is uh, good at 0 volts is transferred efficiently. So NMOS summary is conclusion here is NMOS is good, or we can say strong, okay, in passing logic 0, strong at 0, logic 0, whereas it is bad, or you can say weak, while transferring logic 1 or 5 volts. So 0 volts will be transmitted to the drain side 0, but 5 volts here will not be transferred here. On 4 volts and above of source, the transistor turns off. We have seen here this condition, as you can see that the moment it is 4, so VGS already reached threshold voltage. So the slightly increase in the source voltage above 4, the NMOS transistor turns off. So here slightly above this it will turn off. Example is you may have one more intermediate value, say 4.1. So for that voltage here NMOS will be turned off. So this shows that the conclusion here is NMOS is good at or strong at logic 0, but it is bad or weak at logic 1. So this is what the summary of NMOS transistor. Similarly, let us have a look at PMOS transistor. So PMOS pass transistor, PMOS pass transistor. Let us analyze this PMOS as a pass transistor. So here let us connect a voltage source. Okay, instead of going from earlier we have seen from 0 to all the way up to 5 volts. Let here in this case let us move from 5 to 0 volts. So let us start with 5 and all the way let us move to the 0 volts. And let us tie this to this Vs to the 0 volts, and we'll see that what happens here. And here let us call this as a source, this as a gate, and this as a drain. So VGS, let us see now when 5 volts is connected here, at 5 volts is applied at the source. Let us make a table here. So we have Vs, and next column is VGS, and the PMOS, whether it is on or off, let us write it here. Let us start with 5 volts, and then followed by we have a 4 volts at source, 3 volts, 2 volts, 1 volt, and lastly we have a 0 volts. Okay, so when 5 volt is applied at the source, the VGS is now VG minus Vs, it is minus 5. So transistor is in on state. So the 5 volts is passed here as 5 volts. So we get 5 volts. So 5 volt is at source and you get 5 volts at the drain. So gate is at kept at 0 volts. So VGS now it is at minus 5. It is VG minus VS, 0 minus 5, it remains at minus 5. So PMOS transistor VGS characteristic is somewhat like this. It is like this. Okay. So we have a threshold of minus 1 volt for PMOS, VTP. If we apply more negative voltage, the PMOS conducts heavily. In this case, VGS is, this is the VGS, x-axis, negative x-axis is VGS. When VGS is equal to minus 1, that is VTP, device PMOS starts conducting. For more negative of gate source voltage, PMOS conducts heavily. So as per this, we have VGS now, when VS is at 5 volts, VGS is going to be minus 5. So transistor is on. So the voltage that is applied at source will be available at drain. So this passes 5 volts efficiently. So PMOS is strong at 1 or strong at 5 volts. Let us see other possibilities. When Vs is increased from 5 volts to 4 volts, decreased from 5 volts to 4 volts. Now 4 volts is the applied voltage. Now the voltage at VGS becomes minus 4. VGS is minus 4, where now VGS is increasing. So therefore still the transistor remains in on state. Okay, so 4 volts that we applied, we get 4 volts as output. So no issues with reference to the 4 volts. Even the 3 volts here, we get 3 volts. 3 volts at source, minus 3 volt will be the VGS. Still the transistor is on. 2 volt at source, minus 3 here, this is minus 2 of course. 4, 3, 3 volts applied here, 3 minus 0 is, this is 3, correct? So this is minus 3. 2 volt here, this is 0, this is minus 2. So still the transistor is on. When 1 volt is applied here, now let us see what happens here when the 1 volt is applied. When 1 volt is applied at the source, VG minus VS becomes minus 1 volt. So we are exactly at the threshold of PMOS. As we can see here, threshold of PMOS is minus 1 volt. So now here it is in on and off. It is slowly small, increase in the or decrease in the source voltage will make the PMOS transistor to off. So the moment we go for at least 0.9, so 0.9 volt is not passed here. It remains at 1 volt itself. So if we go for, instead of saying 0 here, let us make it as 0.9. If it is a 0.9, VGS remains at minus 0.9, the transistor remains in the off. So that means we can't send a signal lower than 0.9 or lower than 1 volt here. So PMOS will be turning off. So this shows that the PMOS transistor is good at good, or it is strong in passing 0, strong at logic 0 in sending or passing logic 0, but it is bad or weak. I think I have done it wrong here. Yeah, this is for, yeah, good at 5 volts here. This is my mistake. I'm sorry. So PMOS is good at logic 1, okay, but bad or weak at logic 0. That means 5 volts can be passed efficiently from source to drain, but instead of having 0 volts, we get 1 volt minimum here. So this shows that it is bad at logic 0. So to summarize, NMOS transistor is good at 0, logic 0 or 0 volts, bad at logic 1 or 5 volt, it doesn't pass it. Whereas because it passes only 4 volts here, it doesn't pass 5 volts, it only passes 4 volts. Whereas PMOS transistor It's good at logic 1, it passes 5 volts, but bad at logic 0. It retains 1 volt at the output. When we supply source with 0, drain will have 1 volt. That is the conclusion of pass transistor. Now let us go back to our analysis. So here we have shown the switch representations. The transistor symbols and behaviors are summarized as below. For the sake of simplicity, we indicate a small g for the gate, small s for the source, and small d for the drain. And here we have NMOS transistor symbol, the source which serves as the input, drain which works like an output, and gate is actually the control. Now, keeping gate at 0, so this NMOS transistor behaves like a open switch. So this works like a open switch because gate is 0. For NMOS transistor, gate needs to be 1 to turn on. And when you make gate control as 1, the switch behavior of this is a closed switch. So this works like a closed switch. Now the information here sent from the input side to the output side, it is passed. Okay, so let us see here now. So how it passes. Now let us make this G as 1, and if we apply input as logic 0, output is going to be strong 0. We have already seen this. When input is logic 1 and output will be the degraded one because NMOS fails to transmit 5 volts, that's therefore the output is a degraded one, not a perfect one or not a strong one. That is the quality of NMOS as a pass transistor. Now let us have a look at PMOS transistor. So this is a symbol of a PMOS transistor. PMOS symbol will have a bubble symbol here that shows it complements the input that is applied. The source, drain and gate as shown here. And now gate works like a control once again, similar to the NMOS. Source will act like an input, drain will act like an output here. Keeping control at 0, it acts like a closed switch. PMOS behaves like a closed switch. Unlike in NMOS, G must be 1 to make it as a closed switch, but in case of PMOS, G should be 0 for the switch to for the PMOS transistor to work like a closed switch. Now, whatever the signal, the data we apply at the source, that is transmitted to the output. Okay, whether it is strong 0 or weak, 0 or strong 1 or weak 1, we'll decide it in the next example. But when you make G as 1, the gate terminal is 1. So the switch representation of PMOS is an open switch. So here we have a closed switch for G is equal to 0, and for G is equal to 1 for a PMOS, it behaves like a open switch. Now let us take the closed switch as an example and apply in data at the input and see whether it transmits the same data or not. So let us consider the G is equal to 0 case. This is a PMOS transistor. So let us consider G is equal to 0, and let us apply 0 at the input, logic 0 at the input. And now since G is equal to 0, switch is closed. So output is not a strong 0, it is a degraded 0. We already see the weakness of PMOS transistor. So it transmits a degraded 0 to the output. For G is equal to 1, a 0 once again, when the input is changed to logic 1, okay, now we have a strong 1. Okay, so here the PMOS degrades 0, but it transmits a strong 1. So this is the example that illustrates NMOS and PMOS transistor, how they work like a pass transistor. So that is the theory behind the pass transistor. Now with that we will move on to the transmission gate. Transmission gate is another logic that is constructed with the help of both PMOS and NMOS transistors. So far we have seen the pass transistor, but now we are going to discuss transmission gate. It's also named by another name, which is a pass gate. So what do we mean by transmission gate? So transmission gate is again which passes data from one point to the another point, just like the pass transistor. So here when an NMOS or PMOS is used alone as an imperfect switch, we have already seen that if you use alone NMOS, it is good at 0 but bad at 1. If we use PMOS, it is good at 1 and bad at 0. So we can't use them alone to build a logic circuits. So we have to use them either in a series fashion or parallel fashion to uh, construct the logic circuits. So using alone, they behave like imperfect switch. We sometimes call it as a pass transistor. When we use them alone, we can call them as a pass transistor. Now to build a transmission gate, we need to combine NMOS transistor and PMOS transistor in a parallel manner. So to obtain we obtain a switch that turns on when one is applied to the gate, and which zeros and ones are both passed in acceptable fashion. And we term this as a transmission gate or a pass gate. What do we mean by this? So we need to connect NMOS and PMOS transistors in parallel, and to obtain to a switch behavior, we need to apply the control terminal with NMOS should be applied with 1, and PMOS should be applied with 0. Then we can pass zeros and ones from one side to the other side in acceptable fashion. Here there is no question of degradation, just like in the pass transistor. The transmission gate doesn't degrade the zeros or ones. It can transfer data in acceptable fashion, and these type of gates are termed as a transmission gate or pass gate. Note that the control input and its complement are required by the transmission gate. So transmission gate, unlike the pass transistor, this needs both the control input and its complement. Both are required here. So we need to complement that. Then that will be used as a control to pass data from one point to another point. And this is called as a dual rail logic. Dual rail means we have both a high voltage and the low voltage to control the transmission gate. That concept is, the term is labeled as dual rail logic. And here we have a circuit symbols, and how the data is transmitted from one point to another point, that is explained for the transmission gate. The first is a symbol for the transmission gate is as shown here. We have a upper is going to be the NMOS transistor, and the bottom one is going to be the PMOS transistor, and we have connected them in parallel. So we know that NMOS transistor conducts for 1 volt and the positive voltage, higher voltage, whereas PMOS conducts for -1 and negative voltage. So we have connected them in parallel. So we know that the NMOS transistor is good at logic 0. So 0 will be passed through the NMOS, whereas PMOS transistor is good at 1. So 1 will be transferred through the PMOS transistor, so that the data from A to B is transferred in acceptable fashion without any degradation of logic levels. That means if you have a 0 or 1, the same 0 or 1 we can get it at the receiver side. So provided here we need to have a two complements, G need to be 1 and GB need to be 0. And this behavior is shown in the following examples. So let us see the control here. When G is equal to 0, this G control, if you keep for NMOS, if you keep it at 0, and GB is equal to 1. So this GB, if I keep it at 1, 1 means it is a high voltage. So then this transmission gate behaves like a open switch. So transmission gate behaves like a open switch. Whereas to turn on this transmission gate, G needs to be 1. So we need this condition here, G is equal to 0 and B is equal to 1. This makes the transmission gate in the half mode. To turn on this, the GB needs to be 1 and the GB bar needs to be 0. So the condition is 0. So in such case, the transmission gate will work like a on transistor here, on switch. So here is the A and B. Now let us consider this and check whether this can pass zeros and ones efficiently or not. So now G is equal to 1, GB is equal to 0. We have a normal and a complemented control signal. Input is kept at logic 0 and we have a strong 0. Output is going to be strong 0. Similarly, for the same condition, G is equal to 1, control is equal to 1 and the complement of control is equal to 0. Now let us test it with logic 1 at the input, and the same one as it is transmitted. So we have a strong 1. As I already mentioned it, the ones are transmitted through the PMOS and zeros are transmitted through the NMOS, because the 0, the NMOS is good at 0 and PMOS is good at 1. Okay, so we are able to transfer zeros and ones in an acceptable fashion, and therefore there is no question of degradation here. And here we have an alternate symbols for the transmission gate, as we can club this, the transistors together in a parallel manner, and we can come out with alternate symbol. So G represents its normal output, GB represents its complement output. This is one version of symbol. Another version of symbol is just by writing circle and showing with an into mark. And here normal is shown as a line here, and complement is shown as a bubble here. So this is a complement control signal. A and B are nothing but they are the input and output. Okay, the receiver. So the input is as transmitter and output is going to be the receiver. This is another version of a symbol here. We show with a box type with an arrow mark like this, G and GB as usual, which is a control terminal. A and B are nothing but they are the inputs and outputs respectively. So this is about the transmission gate. Now let us see how to develop, why it is the fully restored logic is used. Fully restored logic is nothing but just like in uh, CMOS we have seen. CMOS we have seen. In the CMOS case, in all our examples, what we have seen is the input is driving the gate terminals of a NMOS transistors in the pull-down network. Okay, in the pull-down network, NMOS transistor drive the output, whereas in the pull-up network, the PMOS transistors in a complementary pull-up network, this is the one which drives the output here. So to summarize here, the NMOS transistors only need to pass zeros from ground to the output. PMOS only passes once, that is from the supply here. Whenever they turn on here, they passes high voltage or logic one from supply to the output here. So the output is strongly driven and the levels are never degraded here. So because input is driven, when based on the input here, the PMOS network passes logic 1 and NMOS network passes logic 0 to the output. This kind of logic is called as a fully restored logic, and there is no question of degradation in the case of CMOS. Okay, and this kind of the fully restored logic simplifies the circuit design in a considerable manner here. That's all about the fully restored logic, and now let us discuss another important circuit called as a tristates. So tristates nothing but a circuit, logic circuit, which is built from transistor, and here the circuit will be in the three states: zero state, logic one state, and its third state is going to be the high impedance state. Okay, or floating state, what we call. So it will be in the three states. A circuit with the three states, 0, 1, and floating state is called as a tristate. The symbol for the tristate buffer is as shown here. So it will have an input and it will have an enable input. There are the two inputs for this. One of them is the primary input, other one is the enable input, and we have only one output here. So this is the tri-state buffer symbol with enable signal here. We have only one enable here. How this works, let us explain through the table here. So if enable is equal to 1, if we make enable input as logic 1, and output will be y is equal to a. Whatever we apply here, either 0 and is applied at the input, the 0 will be transferred, and if 1 is applied at the input, the 1 will be transferred. The y becomes same as a. So that is the buffer behavior. All these things happen because enable is straight to logic 1. So if enable is equal to 0, when you keep enable as 0, what will happen? So output will be in the floating point or it will be in the high impedance state. So once we make enable as 0, then output will be in the high impedance state. Okay, so which is high impedance or floating state here. So we can't use it. It is disabled here. Okay, that's what the behavior of the tri-state buffer with only single enable. Generally, the tri-state buffers comes with the true enables. May the normal enable, which is true, and complementary enable signals, as we can see here, enable and enable bar. This is the normal enable, and other one is going to be the complementary enable here. Okay, so these are the two enable signals that are shown explicitly here. Sometimes we will have only one enable here. Now let us see the working of this one with both enable signals. In this case, we have to apply some signals for both the enables so that to transfer data from input to the output. When enable is equal to 1, this is 1, upper one enable is equal to 1, and enable bar is going to be 0. If this is the case, so the y will be equal to a. This complete buffer will behave like a, this logic circuit will behave like a buffer. So a is transferred to the y. So if it is 0 or 1, the output also will be 0 or 1. So once you make enable as 0 and enable bar as 1, the output will be in a high impedance state. We have already seen this in the single enable, but these things will happen here when enable is equal to 0 and enable bar is equal to 1. So when you keep this as a 1 and enable as 0, so the output will be at the floating point or it will be the high impedance state. So this is the enable circuit logic diagram with the tri-state buffer logic diagram with two enables, enable and enable bar. And we have shown here the truth table for the tri-state buffer. So enable and enable bar, if it is 0 and 1. So A, if it is 0, the output remains at set high impedance or floating state. Because here A is equal to 0 or 1, it doesn't matter. But output, once you disable the enable signal by applying 0 1 0 1 here, these two control signals here, irrespective of the A, output remains at the high impedance state. To turn on the tri-state buffer, we must apply enable as 1 and enable bar as 0. This is the condition for turning on the tri-state buffer. Now the A matters here. Once we applied A as 0, 0 will be transferred here, and when A is 1, the same A will be transferred to Y. So to transfer data from input side to output side, this is the condition required. Okay, this is about the tri-state buffer. Now let us discuss few important things with reference to the tri-state buffer. The transmission gate also has same truth table as a tri-state buffer, but it only requires the two transistors. Okay, so that's why it's called the non-restoring circuit here. If the input is going to be noisy, otherwise it is degraded, the output also will receive the same noise. That is the problem with the tri-state buffer. The delay of series non-restoring gates increases rapidly with the number of gates. So this is a delay with reference to delay. And below we have shown one circuit which is called as tri-state inverter. Let us look at the logic circuit for tri-state inverter. So this is the first is the basic diagram of a tri-state inverter, which has got a PMOS transistor and NMOS transistor at the both upper and bottom, and in between we have one PMOS and one NMOS with input as enable bar and enable. This circuit works like a tri-state inverter. Okay, let us see that for the condition here, enable is equal to 0, and what will happen here. So when enable is equal to 0, so this is 0 here, enable bar equals to 1, these two transistors will be off. This is off, so this is off. The switch equivalent is shown here. The switch equivalent is represented here, shown here. Both behaves like a open switch, so therefore output remains in the high impedance state. So when enable is equal when we apply the opposite to the enable, when we make enable is equal to 1, let us see what happens. And remove this. So when enable is equal to 1, this is 1. Enable bar is going to be 0. So this makes the PMOS transistor on, and also the NMOS transistor will be on. Enable is equal to 1, and their behavior is looks like this. They behave like a closed switch. So now you can see here. So this complete circuit now, after replacing here PMOS and NMOS with a closed switch, the complete circuit looks like an inverter. So if we apply A here, then output will be Y is equal to A bar. So this is the working principle of tri-state inverter. A tri-state inverter used in many, the microprocessor design and even in the CPU design. So it is widely used logic circuit. So this is about the tri-state buffer. It is fully again restoring kind of logic gate here. And let us look at the different applications of tri-state buffer. And this is the explanation of both the tri-state buffer. The applications are, tri-state buffers are used to allow multiple units to drive a common bus. When a common bus is there, when multiple units are driving it, okay, so what happens here? So a common bus is as long as exactly one unit is enabled at a time. So only one can transmit data on the bus. Bus is the thing, but it's a group of wire. So one particular a device can transmit data. What happens if multiple units drive the bus? If the multiple units, suppose if there is a unit 1 here and unit 2, and all of them want to transmit data on the bus, so in such case the contention occurs, and the power is also wasted. So the data is not transmitted properly, so bus will be overloaded with multiple data and we lose data, so power is going to be wasted. And second scenario is, if there are no units to drive the bus, then what happens here? The bus will remain at the floating, and it will have an invalid logic level, and that causes again receivers to waste. Power of the receiver is going to be wasted. And next is going to be the last case. It can be difficult to switch enable signals at exactly the same time when they are distributed across a large chip. Probably when there is a large chip and many wants to transmit some signals. So what happens when the many units transfer the signals? So in such case, the delay between the enables switching can cause the contention. So the enable is very important here when we have multiple signals units are transferring data. Any delay in the enable signal that will cause the contention loss of signal, and so these problems of tri-state buffers can be efficiently addressed with the help of multiplexers or the tri-state buses. So we'll see the multiplexers in the next class. That's all about the pass transistors and the transmission gauge. And lastly, we discussed about the tri-state buffers. Okay. So with that, we'll stop here, and next class we'll go with another video. Thank you all for watching.